अंकुर जी नमस्कार। Am I audible?
Sir, now my voice is audible, sir.
Yeah. Now it is audible. नमस्कार, क्या हाल चाल है?
बस ठीक हो सर।
बढ़िया।
हाँ सर, सॉरी डिले के लिए।
नहीं, कोई प्रॉब्लम नहीं है। Can we start now?
Yes sir.
Okay, so audience, our today's speaker is Ankur Sangan, and Mr. Ankur did their MTech in VLSI design and have 10 plus year experience in the VLSI domain, and he had worked with CDEC as design engineer from 2007 to 2009, and presently he is working with the Coral technology as senior application engineer, and he is working in the domain of the CAD tools and then FPGA based design and many more. He is very experienced person. I personally know him, and he is a very experienced and very good person. He is having a very good knowledge in that field. So Ankur, can you please start now?
Yes sir. Thanks sir. So very good morning to all of you. Just wait. Sir, now my voice is clear?
Yeah.
Okay. So our today agenda is related to the FPGA. So today we will discuss about the FPGA. But before discussing about FPGA, first of all, within one or two slides, I'll discuss about the Coral technology. In this Coral technology, basically we are working in three domains. One is our IP design development and manufacturing, and another one is related to the representation distributions related to the design software like Xilinx and Mentor Graphics. This is separate entity, so Coral providing the support related to the Xilinx and related to the Mentor activity. So if any customer wants any such kind of help related to the designing part, so Coral will provide these supports. And as well as like if any customer wants some solutions related to the design, like they are creating some design, in the design some small domain it is not possible to create for him due to time constraints and due to experience manpower. So these things completely and these type of solutions provided by the Coral. So Coral is working in training domain as well, in embedded and as well as system design. After that, so now this is one small breakup, like which type of products we are dealing. We are dealing with the defense projects and defense projects. Then we are also dealing with the video and related to the some image processing and related to the broadcasting products. So earlier Coral already designed one product for BBC London, name is Stage Box. So Stage Box you can use for the live broadcast. I think all of you are aware with if any live match or if any live broadcasting, so each and every channels or need some broadcasting well. So Coral provide one solution. It is very small solution, 1 cross 1 feet size. This is the solution. You can just directly to attach with the camera, and without any wired connection, you can start your live broadcasting. So these type of solutions provided from the Coral side, and Coral is also working with the government, private sector, and as well as educational institutions. And if we are talking about the educational institutes, Coral attached with more than 3K institutes last near about more than 10 years. So very rich contacts and related to the very rich engagements in our projects with the professors and with the different research teams. And this is some awards and recognition from the government of India. And Coral is also filed near more than 3 to 4 patents. Okay, and Coral already get one award from related in Making in India, top 25 companies, innovative company, and this is completely Indian company. So now we will come our today topic. So first of all, I want to discuss with you related to the FPGA. All of you aware with FPGA? And please, if you have any question or any query, you can ask me in chat room, or as well as you can open your mic and ask me anytime. So all of you aware with FPGA or having some basic architecture knowledge related to the FPGA? Okay, I'll explain. FPGA, this is your programmable unit. Similarly, like you can see microcontroller and microprocessors. So microcontroller and microprocessors, this is also a programming unit. Now, why we are using FPGA? Because in your FPGA options are available related to the parallel processing. So we are discussing about the FPGA and as well as microcontroller and microprocessor. So why we are using this programmable devices compared to microcontroller and microprocessor. So when we are using microcontroller and microprocessor, at that time having lots of limitations in the sense when you insert your design, like when you're writing your design as a source file, so that time you need to use only assembly language, and some microcontrollers it is also supported assembly in C language. But here related to the FPGA, very rich options are available. Like if you want to work with the HDL language, VHDL, Verilog, you can also use it. Or if you want to use some other like C, C++, this is also supported. And currently like OpenCL languages support is also available. Okay, so this is the big difference. So for the designer having more options compared to other one microcontroller and microprocessor. Now if we are talking about the FPGA, in the FPGA parallel processing is available. So like if you want to do parallel processing and number of IOs, if you need 2K or 3K. So that type of input output pins, it is also available in FPGA. Now, if we are talking about the FPGA, in your digital electronics book, you have already learned about related to the PLA, programmable land logic, programmable core logic. So this is the extended version. We can say FPGA, field programmable gate array. So you can directly program your gates. In your microcontroller and microprocessors having some architecture like either 32-bit ALU or 64-bit ALU, and having different such kind of limitations related to the register bank, each and everything. But here everything is open. On the behalf of your gate, you can decide. Now, in the gates, like you can see here mention one name is LUT. LUT stands for lookup table. So with the help of this lookup table, you can implement any Boolean expression. Like I think all of you are aware with, we have some universal gates, NAND or NOR. Why we have called as a universal gate? We can implement any Boolean expression with the help of NAND or NOR. Similarly, we can also implement any Boolean expression with the help of multiplexer. Am I correct or not? Okay. So, so with the help of multiplexer, you can implement any Boolean expression. Similarly, you can implement with the help of LUT, you can directly recognize with mux. You can see internally 2 5 input LUTs are there. So 2 5 input LUTs having 1, 2, 3, 4, 5. This is 5 input pin and 2 output pins. Okay. Actually, older one architecture having only 1 output pin and 4 input pin in 6 series architecture. If you are talking, this is older one. If you have already done some work with the Spartan 3 devices or Vertex 4 or Vertex 5 devices, so in these devices having only 4 input pins and 1 output pin. But here you can see we have 6 input pins and 2 output pins. So now how it is beneficial for us? You can see here, like if you want to implement 1-bit full adder, if you want to implement 1-bit full adder, so in your 1-bit full adder, I think having two equations, so one for sum and another one for carry. So with the help of one LUT, you can easily implement your sum equation, and with the help of another one LUT, it is already available only in 6 input LUT, 5. So with the help of these this one arrangement, you can easily implement, like with one 5 input LUT, you can implement your sum equation, and with the help of another one you can implement your carry equations. Okay, so with the help of only single LUT, you can implement your 2 Boolean expressions, and here number of input pins are more. Okay, so that's why like compared to older one architecture, you can implement bigger Boolean expression in this new architecture. And please, if you feel any questions, any doubt in your mind anytime, you can ask me anytime, please. So now I am discussing about which type of resources are available. So we have discussed about LUT. So we can say here group of LUT with flip-flop. Okay, and other some logic gates we can call as a slice. So group of LUT and some logic gates we can call as a slice. This is mentioned here, and after that group of slice we can call as a CLB. So now you can say CLB, this is the superset of slice, and slices are the superset of LUT and flip-flop. So this is the hierarchical level. Okay, it is clear. So like group of LUT and some flip-flop we can call as a slice, and after that group of slices we can call as a CLB. Now, if you are working with related to the sequential statements or any such kind of, say you need some, in your design you need to intermediate some registers. So you can, you need memory. So this is also available in the form of block RAM, DRAM. This is also available here, memory. After that, your multiplier, this is also available. If you want to work related to the DSP related applications, so you need multipliers and summing. So both are available in the form of DSP4080 slice. This is the name of specific slice. With the help of this slice, you can easily implement your DSP related algorithms. Now, if we are talking about the interconnect resources, so in this interconnect resources, having first one is programmable interconnects. So if we are talking about the programmable interconnects, you can see here, I already discussed with you, FPGA stands for Filled Programmable Gate Array. So you can see, this is the array, and here your CLBs are available. So now, how can you decide? Like here, what we will do when we are programming, we can just enable or disable our CLB or our different logic like slices or LUT. So here we have one programmable switch. You can say this is programmable switch or programmable interconnect. So on the behalf of these programmable switch or programmable, you can say programmable interconnect. Okay, you can just directly to enable or disable, like which one CLB you want to use in your design, because in your FPGA devices this is available 10K, 20K, and it is also available in lakhs in single device. Okay, so so much of complexity available with the FPGA, like no need to take any tensions related, like in my FPGA having limited resources, because here no any such kind of limitations related to the resources, each and every family having lots of different type of devices. Okay, so now we are discussing about IOB. If you want to connect with your FPGA IC any external applications, so you need input output pins, GPIO pins you need it. So this is also available, and this is bi-directional. You can decide you want to use as an input or you want as a output. Okay, you can see here, like this is your FPGA IC. So this externally these pins are available. So this is bidirectional pins. Okay. After your programming and in the design, if you have specified this pin as an input, so it behave like an input, or if you have decided as an output, so it behave like a output. Now related to the other resources, in this other resources, global clock buffers and boundary scan logic. I'll give you some example. Like I think you already aware with some ICs, IC 555. In your IC 555, some pins are but in IC 555, some pin every pin is fixed. VDD and ground. So in that one manner, some pins are fixed related to the clock or reset. So these pins are fixed. You cannot change. Okay. So similarly, your clock buffer pin, it is also fixed. So with the help of this global clock buffer pin, you can easily change, or you can easily maintain your clock. Like if you want to give any delay in your clock path, so these things you can easily manage. Boundary scan logic and JTAG, with the help of these technique, this is also available inbuilt in your FPGA device. With the help of these things, you can just check how much programmable space is available. Like for your programming, how much space is available. With the help of this space, you can easily utilize. Okay, so these are our resources available. Please, if you have any questions or any doubt, you can ask me. Or if you want, please explain this one portion again. I can explain again. No issue. Any doubt? Okay. So now we are discussing about the SoC, system on chip. So in this SoC, SoC. So in this SoC, you can see here two portions are available. One is your PS part. So in this PS part, your ARM Cortex processors are available, and in this PL part, your FPGA portion is available. Okay. So you can see here, we can call as a SoC. SoC stands for system on chip. So with the help of this system on chip, now in your FPGA IC having both options. Like if you want to, if you have create some design, okay, and in your design having some portion is A and some part is B. So two different teams are working. So A team design on the behalf of assembly language, and B team work on the behalf of VHDL and Verilog. So both portions, if you want to integrate on any hardware, so you can use this Zinc SoC family, system on chip, because here your PS part, like your ARM ICs are available, ARM portion is available, ARM Cortex A9 processor is available, and in Zinc Ultra Scale this is also available. So currently in your mobile having A53 ARM processor, or some devices having A72 processor available in your devices. So such kind of similar processor available in your Zinc Ultra Scale devices and Versal. This is new one devices, okay, and these devices are available on 7 nanometer FinFET based technology, and these 7 series SoCs are available on 28 nanometer CMOS based. Okay, and so this is the common specification. These different ICs are available in this family. Okay, so with the help of these different family, you can see here resources are different. Number of logic cells, lookup table, flip-flop, and your block RAM, DSP slices, each and every capacity is different in your ICs. So it depends on your requirement. In your design requirement, you can just directly to decide which one IC is more suitable. If you have any doubt or any questions, you can ask me anytime. So So now you can see here, this is the basic alignment in your 7 series architecture. First of all, your CLB. So if we are talking about the CLB, in the CLB internally slices are available, and internally in the slices, your LUT and flip-flops are available in red one portion. After that, BRAM, this is your block RAM is available. Okay, green one, this is your block RAM. Then your IO, this is your input output pins. Actually, Xilinx already given input output pins is 2 types. One is your high performance pins and another one is your high range pins. So if we are talking about the high performance pins, we can call here as a MGT. MGT stands for multi-gigabit trans receivers. This is available here, and this is your HR pins, yellow one. This is available here. Now, if you are talking about what is the difference between your HR and HP pins, like if you want to work with more than 2 Gbps speed, so you need to use your MGT pins, multi-gigabit trans receiver pins, or otherwise you need to use your yellow one part, HR pins. And in your critical ICs having MGT pins are more, but if you are talking about like for the normal industry or home automation industry, they are using maximum time HR pins, high range pins, because applications work maximum more than less than 2 Gbps speed. Okay, so this is your related to the input and output information. Now CMT, clock management tile. See, in your design, this is your complete system, and in this system having different portion. This is your A, this is your B, this is your C. And our complete system requirement, for A you need 10 megahertz clock, for B you need 40 megahertz clock, for C you need 20 megahertz clock. Okay, so these different clocks you need it if you want to run this design. So with the help of CMT, you can generate your multiple clock internally. No need to take any tensions. The CMT automatically manage, and CMT work in 2 criteria. One is MMCM, mixed mode clock manager, and another one is PLL. PLL stands for phase lock loop. Okay, so on the behalf of these 2 different approaches, CMT is working. Now FIFO logic, if you are using some resources in cascaded mode, okay, so FIFO it is available to manage these things, this one portion. Now BUFG, if you want to give some delay in your clock path, so with the help of BUFG you can maintain. This is available here. After that, DSP related things, multipliers and summing. So with the help of these multipliers and summing, it is available in the form of DSP48E related to the DSP related operations. Now BUFIO and BUFR, this is very important thing. I think all of you are aware with how many paths are available in your digital circuit, in any digital circuit. Maximum how many paths are available? My question is clear? In any digital circuit having maximum okay, we can see how many different type of paths are available. We can just draw one circuit. This is some A logic, this is some B logic internally. It is connected here to here. This is input to register. This is register to register. This is register to output. And this is input to output. Okay. So in your any circuitry having maximum 4 type of paths. No any 5th path is available. One is your input to reg. This is your reg to reg and reg to output. And after that, input or output you can say, or output to input. This is like a feedback path. Okay, so maximum 4 type of paths are available in any digital circuit. So if you want to create these different paths with the help of buff IO and buff R, you can create these paths or these connections in mid of your CLBs. Okay, so is it clear? If you have any doubt, you can ask me. Any doubt? So now you can see slice M and slice L. So if we are talking about the slices having 2 types. One is your slice M and another one is your slice L. Slice M you can use for memory related operation and as well as logical operations. So we can also call as a full slice because we can perform any operation with the help of this slice related to the memory and related to the logic. Shift register logic, if you want to use as a shift register logic, you can also use it, this slice M. After that, related to the slice L, it is working on the behalf of logically or arithmetic operations. Only 2 type of operations you can perform with the help of slice L. Each and every device having slice L 75% and 25% it is slice L. This is the on an average ratio. Maybe 1 or 2 like from here to here, it is different scenario. But generally slice M this is 25% and slice L this is near about 75%. So this is the ratio mid of your slice M and mid of slice L. So now you can see this is the internal architecture of single slice. So internally in this single slice architecture, you can see here we have 1, 2, 3 and 4. 4 different LUTs are involved in your single slice. Okay. After that, multipliers and carry chain. This is also available. Now, not multiplier, multiplexer. So if we are talking about the multiplexer, this is available here. Why we are using these multiplexers? So with the help of these multiplexers, it is just directly to controlling the output of LUT. Okay. After that, your carry chain. It will help for the cascaded circuit, like if you want to use in a same circuit your 2 LUTs and 2 different like LUT, those are all having in different slices, so you can also access. Okay. After that, related to the flip-flop, so you can see here 1, 2, 3, 4, 5, 6, 7, 8. So 8 flip-flops or 8 latches, it depends on your IC configuration, which one is available. And in these 8, each and every 4 bunch having common clock connection and common set or reset connection and common related to the clock, chip enable or set or reset. These signals are common. Like if you want to enable this one flip-flop with the help of these 3 signals, so these 3 flip-flops automatically on. Okay, so this is the limitation internally in the slices. Either all are enabled or either all are disabled. Any questions? So now we will discuss a little bit about the ultra-scale devices. So in these ultra-scale devices having Kintex and Vertex ultra-scale devices. So these ultra-scale devices are available on 16 nanometer FinFET based technology. Okay. So here resources are more compared to older one technology node. So if you want to see the differences between older one and new one, so you can see in that one manner resources are more in your ultra scale family. This is the architecture of Zinc. So in this Zinc 7000 and Zinc 7000 ultra scale. So if we are talking about this Zinc 7000, so in this Zinc 7000 you can see here we have ARM Cortex A9 dual core processor, and these processor connected with your different protocols. Okay. After that, this yellow portion, this is your PL part. So in this PL part, your FPGA logic is available, and both are tightly bound with the AXI light bus in the Zinc 7000. If we are talking about the Zinc Ultra scale, okay, so in this Zinc Ultra scale, having ARM Cortex, application processing unit having ARM Cortex A53, and here it is bind with the help of AMBA AXI 4 bus, and here having AMBA AXI light bus in the Zinc 7000. Okay, so you can see in this PS part, lots of different processors are available related to the graphics, related to the security, lot of things are available. Okay, so this is the layout of your SoC. So now up till what we have discussed about we can just summarize. We have discussed about the 7 series architecture. So in this 7 series architecture, we have discussed about the LUT. This is 7 series architecture having 6 input LUT. Okay, so 6 input and 2 output. One output work on the behalf of 5 signal, and one output works on the behalf of 6 signals. So these things we have discussed. LUT you can directly realize with MUX. So simply if you want to implement any Boolean expression with the help of MUX, similarly you can also implement your Boolean expression with the help of this LUT. Okay, then we have discussed about the logic resources. So in the logic resources, we have discussed about the slices, group of LUT and flip-flop we can call as a slices, and group of slices we can call as a CLB. So these things we have discussed, and after that we have discussed about input-output bank. It is divided in 2 parts, HP and HR. HP stands for high performance pins, HR stands for high range pins. So if you want to discuss about the differences, high performance pins, if you want to work with more than 2 Gbps speed, then it is supported up to 1.8 volt. And if we are talking about related to this one, Zinc 7000, it is supported till less than 2 gigahertz. Okay, so in that manner, support is available related to the input output. So after that, we have discussed about the clock management tile, CMT. Clock management tile, it behaves on 2 different you can say algorithm. One is PLL technique, phase lock loop technique, and another one is MMCM. MMCM you can use as a black box. Actually, this is the patented thing for Xilinx. But if you want to use in your design, you can use free of cost. So these things we have discussed. Then we have discussed about the Zinc SoC. In the Zinc SoC, we have seen ARM Cortex A9 dual core processor with your FPGA space, and in this FPGA space having lots of different resources are different. Okay, so these things we have discussed. So if you have any doubt or any questions, you can ask me. Yes, anyone ask any question?
Excuse me, sir.
Yes.
Sir, what are IP cores FPGA?
IP cores IP core in the sense related to the processors you asked me, or related to the logic core library?
Sir, in both the ways I am asking about the IP code, sir.
So if you are talking about related to the physically, which one processors are available, ARM Cortex A9 processor available in your Zinc family. If you are talking about the Zinc Ultra Scale having multiple processors, A53, ARM Cortex A53 processor is available, R5 processor is available, okay. Then graphic processing unit, Mali processor is available. So these different processors are available in your single IC. Okay, now if you are talking about the logic core, so in the logic core, having 100%, 100 plus different IPs are available. IPs in the sense like basic element IPs, counter related to the image processing, Ethernet. So these different devices are, these different IPs are available, and it is already integrated in your Vivado window.
Okay, sir.
Is there any other questions? You want to ask any other questions? Okay, so I'll give you one small quiz. This is only for like those things I have discussed. On the behalf of these things, I have just prepare one small quiz. You can just reply, and within a 2 to 3 minutes, I'll just prepare my system for the demonstration, one small demonstration related to the Vivado toolset, how it is working and how you will do if you want to do some delay calculation or thing. So 2 to 3 things I'll discuss with you in the demonstration part. Okay. So meanwhile, you can do one thing. You can try to solve this quiz. And this is not a, like it depends on you as you wish. If you want to fill, you can fill. If you don't want to fill, no any such kind of compulsion, like some part will add in yours related to the certificate. Okay, no any such kind of compulsion related to these things. But if you solve this quiz, this is helpful for you. Okay, so now I can open Vivado toolset. Actually, it will take some time, because now in the new Vivado toolset related to the AI, related to the machine learning, IoT, lots of new library already added. So if you are talking about new version size, this is more than 90 GB if you installed in your machines. So it will take little bit time, because you need minimum 32 GB RAM for your machine if you want to work on upgraded one. Upgraded Vivado version. So, and any one of you already done some work with FPGA in past, or currently you are working on FPGA?
Sir, implemented only few basic logic gates and some basic programs on FPGA.
Okay. No any such kind of targeted applications, like you want to develop some application related to the DSP area or related to the embedded area. Because one more interesting thing is available. ARM also providing soft IP core like ARM Cortex M1, M2. These are all available from the ARM side. Freely available IPs. So if you want to dump these IP in the FPGA board, you can also dump, and after that you can use it. Any one of you try to solve this quiz? Okay. No. Nice. So you can see this is the Vivado window. So in this Vivado window, you can click here on create project. And currently in the new Vivado version having TCL support, it is also available. Like if you want to run in a scripting mode, you can also run. That one option is also available. So you can click on next button. Now you can give your project name. So if you want to change the location in your machine, you can change here. But when you are selecting your path or anything, okay, so just remember, don't give space in your path and don't use a special character except underscore. Okay, so these things you need to take care. We can just run one simple combinational circuitry. So RTL project do not specify source at the time. Now you can click on boards. In this board, actually pink Z2 board is available. So we can. If it is not available showing in this list, so you can go to the family, Zinc 7000, package, this is CLG 400, speed it is -1. But if you want to check on internet, like you have selected perfect combinations or not, so you can do one thing. You can select here pink Z2 board. You can just type here name. Okay. So when you type here name, after that, you can see here XC7020 CLG 400. So you can select this configuration. XC7020 CLG 400. Now if you want to see how much resources are available, this is your IOB pins, LUTs, flip-flop. Each and every resources you can check how much it is available with your device. If you are talking about clock manager, so it is available 4. Okay, now click on next button, finish. Okay, so you can click on add source. Option is available, add or create design source. Then click on next button, create file. So if you want to create in Verilog, so you can just define here name. And when you are giving your file name, don't use space and don't use special character except underscore if you want to use. If you have knowledge related to the database, so I think you already have MySQL or some different database not supported related to the special character, because special characters are available as a keyword. A, comma B, comma C. This is your input, and sum, comma carry. This is your output. So you can select here. Now you can click on OK button. Assign. Sum equals to A, XOR. This is the symbol of XOR in Verilog language. Okay, so you can save this. Now you can run your simulation, so you can click here to run simulation, run behavioral simulation. Please, if you have any doubt or any questions, so you can also ask me in chat if you want. It will take 1 minute time. So now you can see here, this is your simulation window. So in the simulation window, if you already written in the task bench, so you can directly press this run button, or otherwise you can do one thing. You can select your signal, right click, force clock or force constant. With the help of these options, you can just insert your input vectors. So you have selected here force clock. 20. हेलो, यस सर। सर मैं आपको कॉल करता हूँ थोड़ी देर में। So you have already filled your input vectors. After that, you can press this run button. Then you can see all simulation results. Okay, so these different results, you can see all the vectors, like all the test cases. This is your 0 1 0, this is your 1 0 0, this is your 0 0 0. So in this 0 0 case, output it is also 0 0. So in that one manner, you can easily visualize your results. So now go to the file, close simulation. After that, you can click on open elaboration design, open elaborated design. Basically in this open elaborated design tool will check, is it possible to convert your design in RTL or not, in this option. So once we will check these options, okay, so अभी करता हूँ 15. So you can see in this RTL analysis, open elaborated design. So it is just directly to checking. It will be convert our design in RTL or not. I need 10 to 15 minutes more to complete this flow. Because this is 12 o'clock, so that's why. So you can see, if you want to see the schematic, so you can see this is your RTL schematic. Okay, so how you will check this is RTL based output schematic. So each and every block available with one prefix RTL underscore, and here no any buffer. Once we have done our synthesis, then we can see buffers, it is also available. But before these things, what we need some information, or we need to put more information related to our hardware environment. Like we have 3 input signals, ABC, sum and carry, 2 output signals. Okay, so in your FPGA IC having more than 200 pins and more than 2K pins. Okay, so which one pin connect with which one port? So these things you can check. I can also visualize. You can see this is the FPGA board. You can see this is the FPGA board, pink Z2 board. Okay, so in this pink Z2 board, this is the box. So we will use this demonstration, this one board. So in this board, you can see This is your board. Under this heatsink, your FPGA IC is available, and these GPIOs are available. And in this board, Raspberry Pi connectors is also available. Like if you want to connect in future with Raspberry Pi board, you can also connect. Okay. So Ethernet, that one is also available. You can use it. So now what we need to do, we can specify related to these GPIO pin number in our design. So how you will get this information? So if you want to get this information, you need to just mention in your Google PINC Z2 master XDC file. So this is available here. Extract here. Okay, PINC XDC. This is the name of file. Yes, this is available here. So you can see here related to the LED or switches we needed for our design. So you can see D19, D20 and L20. So you need to put this information. L20. R14, P14. This is for output. R14, P14, yes, and so all are working on IO standards LV-CMOS 33. So you need to select here. LV-CMOS 33. Actually, these LEDs and switches are working on 3.3 volts, so that's why we need to select here LV-CMOS 33. This is the IO standard. After that, you can do one thing, you can directly click on generate bit stream. So it will automatically generate your bit stream. Now you can see one beautiful option available in the Vivado toolset, number of jobs, 4. So currently in my system having 4 codes are free. So it is automatically converted in your 4 parallel operations, complete process. So it will run automatically. You can see here process bar it is showing. Once it will start. Currently synthesis is running. doubt or any questions in your mind, you can ask me if you want. Okay, some of you I think learn lot of things because all answers are correct. Okay, synthesis is completed. I can also show you the report. So you can see here report utilization. So you can see, and this is very beautiful report. Like you can see each and every resources like related to the memory, anything, because it is not showing here. It is no any use for related to the TSP or related to the memory. So no any element it is selected. So and in the summary you can see the total utilization. Number of input output banks only 5. So it is available 125 input output pins. So this utilization only 4%. So if we are talking about the LUT, it is only 1. So with the help of one LUT, you can see it is already implemented both equations, LUT. Now with the help of this is sum and carry, and here buffers it is also available. So it is just directly to map your on the behalf of resources, those resources available in FPGA IC. All of you aware with what is synthesis? You can just directly to map your logic on the behalf of your library, cell library. If you are talking about the ASIC, so your library is ASIC cell library. And if you are talking about the FPGA, so FPGA IC resource library. So these things are there. Now, if you want to do related to the delay simulation, so once it is, we can start this related to this post timing simulation. If you want to do, so you can click here, run post implementation timing simulation. Or if you want to see the physical location, like which one cell it is selected. I'll show you later. First of all, I'll show you how you will do related to this delay simulation. So you can see this is your ABC, this is your input. So in the similar manner, you can put again signals. Okay, so when you press this run button, you can see here all the results. Now, if you want to do some similarity, if you want to do some related to the delay. So now if you want to see delay A2 sum or A2 carry, so you can do one thing. First of all, you need to select this A signal and with the help of these options, this is for previous transition and this is for next transition. So you have selected this A signal and you want to go for next transition. This is your yellow marker. So you have already settled flag here. So you can just add here marker. So you have already added here marker. Now if you want to see A2 carry delay, so you need to select your carry and after that go for next transition. So you can see carry here. So when you have click on blue line, so you can see it is showing here delay value. So in that one manner, you can calculate delay. Okay. So is it clear to all of you? Now you can go to the file, close simulation. Now if you want to see the physical locations of LUT, you can see when you click on LUT, it is automatically highlighted. So it is available in this region. In the slides, I have already showed you same image. This is your flip-flops, this is your LUT, this is the slice diagram. Okay. If you want to see your connections, so you need to click here. So you can see these yellow one wired, these part, it is selected by the tool for these connections with the buffers A, B, C and some carry. Okay. So you can easily visualize. Now we have already generated our bit stream. Open hardware manager. I already connected the board, so you need to click on open target, auto connected. Allow access. So you can see this is the board, it is connected through here. At that time it is scanning like how many programmable devices are available. In this window you can see. Actually, we have connected some other like version, so maybe it is showing some problem, but it will take time because lots of different version we need to install. So then you can click on program device. This is available here, this tab, program device. So on the board, one LED will glow once it is programmed. Yeah, green one. So now your design already dumped in this FPGA board. So with the help of these push buttons, you can verify your logic at the time. All are one. So sum and carry, both LED is glowing. So when A or B is 1, so carry 1, sum 0. If only one LED, one switch you have pressed, so sum is 1, carry 0. So in that one manner, you can verify your logic. Or currently, like when you have dumped your application in the board, so if you want to check temperature or anything, so here one XADC system monitor is available. So with the help of this XADC system monitor, you can run. You can see these results. Okay, so now from my side it is over, but here is having lots of options are available in this FPGA. Like if your if you have implemented some algorithm, and in your algorithm having more than 500 pins. Okay, so if we will provide you a switch and LED on the board more than 500 or 200, you cannot verify your all the test cases. You need more time with the help of switch and LED. Okay, so in that one case, internal logic analyzer is also available. You can use it. So lots of different approaches are available. You can verify. So from my side, it is over. Like if you have any questions or any query, you can ask me. Yeah, you can select these things from the manuals as well, FPGA board. And if you don't have any such kind of manuals, so you can do one thing. You can just type your board name. Like if you are using Z board, so you can just type here Z board plus master XDC file. You can just type on Google. Then like if Xilinx make boards are available, or Xilinx sister company concerned boards, so each and every board XDC, master XDC files are available on internet. You can download on GitHub, it is available. So this is your Z board. Any such kind of board you can select. So in that one manner, after that, one another questions. Is IP core is the part of processor, or processor is the part of IP core? Actually, both things are separately. Separately means like, but one thing related to the processor, some IP cores are available. So if you want to configure your processor through IP core, you can also do that. That one option is also available. And if you don't want to use your IPs for processor, that one option is also available. Some IPs are available. You can directly dump in your FPGA part. Like I already described, in this device is having two different parts. One is your FPGA one, and another one is your ARM processor part. So for both portions, having different IPs are available. If you want to see in the software, it is available here, IP catalog. So in this IP catalog, you can see lots of different IPs are available, and these IPs are more than 100. Basic elements related to the automation, audio, so related to the AXI interconnects. So these things are available. You can directly utilize in your design. Oh, I think your question is clear, Sushil ji.
Yes, sir. Thank you, sir.
Sir, related to the learning a Verilog language, sir, you can use textbook Samir Paletkar, or otherwise in YouTube, lots of different lectures are available, or NPTEL lectures is also available. you can refer these material. Okay. So if you want to ask any other question, you can just type in chat room. Okay, so now from my side, it is over. Okay, so if you have any questions or any query, you can also drop me a mail. This board support Python. Yes, it is supporting Python, but one more thing. Python, this is the scripting language. This is not a general programming language. So with the Python, you are using as an interpreter here. Okay. And if you want to learn about this platform, so you can see eyq.io. This is the website. You can learn about Ring platform. So how you will use. I already typed website link on chat room. So any other questions or any query you can ask me related to the FPGA or related to the EDA if you want. Yeah, TCL language, if you are talking about the TCL language, because like if you want to press lots of time, same option or same constraints, okay, so you can easily give through you can easily give through TCL scripting, or if you want to see, I can also show you here. Now, one of you asked me one question related to the AI. Yes, AI stuff is also available. The form is available. My screen is visible, so I can show you. This is VTech in the IP catalog, and you can directly use in your design. AI related to the machine learning and DPU IPs are also available if you want to work on deep learning. So that one is also available. You can use it. Or if you want to see, I can
Hello, sir.
Yes.
Sir, any specific
Yes.
source or useful source to learn the TCL language, sir?
Sir, for the TCL, like lots of different resources are available on YouTube. You can check. Or otherwise, some TCL related, like first of all, na, sir, you need to decide for which approach you want to use TCL language. Because TCL related, na, lots of stuffs are available. Like for the if you are talking some website developer, they can also use it. If you are talking about in our industry, like those are all working related to the FPGA or design. So you need to try, like if you are using some tool, if you are using some EDA tool, so in the EDA tool you can just try to run some options with the help of TCL scripts. Or if you want to check on Google, lots of different examples are available on different website, and some TCL 24 hours crash course is also available. Like 24 hours books are available, Pearl 24, TCL 24 hour. So you can also work if you want.
Yes, Perl and Shell scripting is also good option.
For the shell programming, if you are talking about Yashwant Kanitkar, related to the basics. I already shared one link related to the BTS AI platform. So in this platform, complete AI, machine learning, deep learning support is available. But actually, as a logic core library, these different IPs are available in the manner of IPs. You can use it. RF SoC, 5G communication, that one support is also available in another board, not in this board. So now, if you have other doubts, you can ask me. Okay. Okay. My session is over from my side. Okay. And in future, if you want to ask any questions, you can ask me through email. This is my email ID and this is my contact number. But first of all, try to contact through email, because lots of time I am in trainings or any other work, like lots of time involvement in different activities. So if you will send me an email, I will reply within 24 hours or ASAP. Okay, so thanks all of you.
Okay, thank
What
you.
is the difference? Yeah, what is the difference between slice register or slice LUT? Actually, in your slice register, basically we can call as a slice M, I think so. And slice LUT you can call as a slice L. In your slice L, you can perform only arithmetic and logical operations, and your slice M you can also use as a memory or as a distributed memory. You can use it. This is the difference. Okay, so
Okay, sir. Thank
any
you.
other?
Okay, sir. Thank you.
Yeah, welcome, sir.
Hello, Jitendra sir. Ravi. Okay. In after 5 minutes we will start. Okay, no problem. Okay.
हाँ जितेंद्र, डॉक्टर जितेंद्र।
हाँ सर, प्रेजेंट है सर, जितेंद्र सर।
वॉइस नहीं आ रही।
जितेंद्र सर, यू आर नॉट ऑडिबल। मैं भी सर वहां पे नहीं है, मैं अभी 5 मिनट का टाइम मांगा। आफ्टर 5 मिनट
आप स्टार्ट करवा लेना, मैं तेरा मीटिंग में हूँ, है ना?
ठीक है, ओके ओके सर। हाँ साहिल, ठीक हो गया। Next speaker is Dr. Jitendra Singh. He is currently working as an assistant professor in Department of Electronics and Communication Engineering at National Institute of Technology, Sikkim. Also, he was worked in the same position in the Department of ECE at NIT Kurukshetra from 12 to 13 and NIT Jalandhar, Punjab from 2013 to 15. He received his BTech degree in Electronics and Communication Engineering from Uttar Pradesh Technical University, Lucknow in 2009 and MTech degree in Microwave Engineering from University of Delhi, New Delhi in 2012. He received his PhD degree in VLSI Design from VR Ambedkar National Institute of Technology, Jalandhar. Dr. Singh has published more than 15 research papers in reputed international journals, and also he has published several national international conference papers and book chapter in the recognized societies. His research interest includes memristor devices, novel advanced semiconductor devices, TFATs, analog digital VLSI design, and most device-based sensor design. So let's start, sir. Jitendra sir.
Yes, thank you, Ravi. Thank you for introducing me. Is my slides is visible to you?
Yes, sir. Yes.
Okay. Okay. So first of all, I would like to thank the Department of EC NIT Jalandhar, especially the coordinator of this course, Dr. Mamta Khosla and Dr. Ashish Raman, for organizing such a useful STC on recent trends in IC and applications. I am so honored to deliver the expert talk on the memristor and its memory application in this session. So actually, first of all, I will talk about the memories, the need of the memories. You can see that you cannot imagine any electronic gadgets in the recent time which have no memory. Each and every equipment needs some memory part, either it may be primary memory or secondary memory. Primary memory are your ROM, RAM, ROM, it may be EEPROM or PROM, or it may be DRAM. In the secondary memory, it is the storage memory, it may be flash or the hard disk. So each and every device, each and every gadgets or appliance, you can see that it may be automobiles, it may be computer, mobile phones, printer, speakers, everywhere you can see that there is a memory part, and you can see that when the part of the memory means the storage capacity is increased, the value of that gadgets will also increase. When you are going to purchase a mobile phone have a 2 GB RAM have the smaller cost as compared to 3 GB RAM. There is a almost 5 to 6,000 difference only for a 1 GB RAM. So the RAM, it may be static RAM or dynamic RAM. It is very useful for the electronic gadgets. So it is a very basic requirement to develop the memory part as we are researching, as we are going through the new technology. So, but it is seen that as the advancement of the new technology in the transistor side, the memory are not developed so fast as the transistor is scaled down. So there are basically certain challenges in the recent memories. We can see that in the SRAM, which is basically, if you want to design a SRAM, you need at least 6 transistors. So in order to store a single node, single 1 or 0, you require 6 transistors. So SRAM has a very low density. Also, you can see that it is volatile in nature, and volatile in nature means when we off the power, the storage charge, the storage information will lost. Also, it is sensitive to process variations. If you talk about the DRAM, so DRAM is also, you know that the scaling of the capacitor in the DRAM is very difficult. We can scale down the transistor in the very at the 22 nanometer or 10 nanometer the node, but it is very difficult to scale the capacitance or capacitor of the DRAM. Also, if you talk about the flash memory, you can you know that in flash memory we have a floating gate, which is sandwiched between the your main gate and the transistor and your transistor part. So basically it is sandwich inserted between in the silicon dioxide in the SiO2 layers. So when we apply a high voltage at the gate, at the main gate, the inversion layer will create at the silicon and silicon SiO2 interface. When we apply a high voltage, then some of the inverted charges are introduced in the floating gate. So when the charges are available in the flash, it is programmed as a 1. When there is no charge in the floating gate, it is programmed as a 0. So these are basically, you can see that there is limitations of this floating gate. It cannot store much charge, and it is also require a very high voltage to program it. Means you need to apply a very high voltage so that the inversion layer charges are introduced in the floating gate. So this is the basic limitations of your conventional memories. Also, you can see that when we scale down our nanotechnology, our transistors, there are the many short channel specs are appears, and we know that our conventional memories are relies on concerned memories are rely on the these transistors. So whatever the short difficulties are arises uh, in the most transistors, these are also reflected in the memories. So there is need to advance some novel memories. So there are the certain memories are evolved throughout over the year, like the phase change memory. In the phase change memory, the low resistance state LRS and high resistance states HRS are basically sensed by the sensing the crystalline and amorphous state of the chalcogenides. So basically, the chalcogenides is the material. So it is when we realize the HRS, it is amorphous, and when we realize it as a low resistance state, it is the crystalline in nature. But it is seen that it is temperature sensitive. When we move from low temperature to high temperature, this causes an undesired phase change. Means it may be changed from crystalline to amorphous and amorphous to crystalline. So it may be shows the undesired phase change. Also, we have another memory that is known as FERAM, ferroelectric random access memory. So there is no difference between there is a only difference between the DRAM and the FERAM. That's the capacitance of the DRAM is the material, the insulating material of the DRAM. Capacitance of DRAM is replaced by the ferroelectric material. So in the ferroelectric materials, what happens when we apply a voltage across it? The dipoles are polarized oriented. So if they are oriented in positive directions, then it shows that is programmed as a LRS state, and when it is negative polarization, it shows the negative polarization. It represents the zero or high resistance state. So, but there is also certain limitations of the FERAM, as it shows the low endurance. Low endurance means ability to retain the R off and R on greater than 1. Basically, this is the basic parameter of any memory device, endurance. If R off by R on ratio will not sustain for a much read and write cycle, then the memory has no use. So it is basically needed that it should retain the R off by R on ratio more than 1, so that it should be switched from high resistance state to the low resistance state. And other memory is the spin transfer torque random access memory, which basically uses the spin polarized current. The spin polarized current is the basic. We know that the current in our electric current we have the 50% up spin electrons and 50% down spin electrons. But if the either of one up spin electrons or down spin electrons are more, then it is called the spin polarized current. So STT-RAM is basically use the spin polarized current to change the orientation of the two magnetic layers, which are separated by the metallic layer. If the orientation of the both layer are same, then it is called the low resistance state. If the orientation of both magnetic layers are different, then it shows the high resistance state. But it also requires basically since it is a current-based phenomenon, current-based mechanism, so it is also have the thermal instability and scaling limit, because the tunneling junction, the magnetic layer junction should be very thick. So it is also the scaling problem. And another one is the memoristor, which is also known as the resistive RAM, which stores the memory in terms of the resistance values. So it is basically not a charge dependent memory, it is basically a state position dependent memory. So today I will discuss about the memoristors and its memory applications. So why we should use memoristor? Basically there are the various virtues of this memristor, which shows the potential applications in many areas. So first of all, it has the excellent compatibility with the CMOS. Basically, whatever the new device is invented, it should be shows the same fabrication processes and same fabrication steps as we have the CMOS processes. But if it has the different, if any device which is recently invented have the any novel process fabrication steps, then it may require to set up another fabrication lab and fabrication techniques, which has a very difficult task, and it is cost more and very time consuming. So because if you want to set up foundries with the novel techniques, fabrication techniques, it requires more and more time, and also it requires a huge amount of the cost. So the memristor, it is the device which shows the capability with the CMOS processes, and it is general. The fabrication step are same. We have the CMOS processes. Also, it has nanoscale sizes. You know that the first memristor which is fabricated in 2008 by the HP lab, it is only 10 nanometer dimension. So you can say that it is seen that as the dimension of the memristor is scaled down, its memristance is increased. So as it is a very nanoscale size, and if we use in the array, in the cross array structure, then it has give the high density. And another is the non-volatile memory. Another property of this memristor is non-volatile. So basically, it retains the resistance state instead of the charge. So if any memory which relies on the charges, then we can see that we know that the charges will dissipate with the time. But the non-volatile memory, but here the memristor, we memorize the last resistance state. So it is easily it cannot dissipate with the time. And when the power went off, it is stored the last resistance state, and when the power back, it will return. It will start with the same position. So these are the basically important properties by which it can be used. Another is it is basically synapse. Used as the synapses of the neurons. Synapses is the junction where the two neurons will communicate to each other. So it will also work, and it is the basic, very important, and recently very much researched field of the memristor for the neuromorphic computing and your neuromorphic logics. And it also gives the fast and low power operations, and it has a simple basic structure as we saw in the later slides. And so it can say that it combines the speed of the SRAM. SRAM has the highest speed in the memory, and density of the DRAM, and also it includes the non-volatility of the flash. So it combines the all virtues in a single memory. So we start with the memristor. What is the memristor? Basically, you know the four electrical parameter, that is voltage, flux, current, and charge. These are the basic four parameters. And if we combine them, if we have 4:2, it will give 6 relations. But it is seen that there is one relation is missing. We can see that the voltage and current is linked by the resistance. Also, we have the relations between the flux and the current by the inductor. Also, we have the relation between the voltage and the charge by the capacitor. And we can also link the voltage and the flux by the Faraday's laws, and current and the charge by the continuity equation, that is I is equal to dq by dt. So, but there is no direct relation between the flux, between the charge and the flux. So In 1971, eminent professor Dr. Leon Chua noticed this missing link, and he propounded a new nonlinear circuit element and named it the memristor. So memristor is the device which has the memory as well as the register. It is basically a register which can retain the memory. So it is basically devised as the four fundamental component apart from the inductor, capacitor, and the resistor, and named it the memristor. So it is basically four fundamental component which is not realized by any another elements. Uh, and he given the basic equations for the to characterize it. So here you can see that its IV equations. Here the resistance is a state dependent variable. Means it depends on the position. So and position itself it is a if the derivate it the position, then it will give the current. So ideal case for the ideal case we can assume it as the W position is as a charge. So if it is charge dependent, then dq by dt is I and r it is rq, means the resistance is charge dependent. But here we use the position instead of the charge. And in 1976, he generalized the concept of the memristor, and he defined as memory systems. And he told that if any device which is governed by these two equations, which is realized by these two equations, that is the resistance is a position dependent as well as the current the current passing through it dependent. Then and the derivative of this position is also a function of the current as well as the position. And then this device is these devices are basically comes into the category of the memory systems. Apart from this, he also suggested the fingerprint of any of a device. That is also includes the fingerprints that which are the if we apply for a device, if we apply a periodic signal, not the DC signal, if we apply a periodic signal through it, then it always form. If you plot the current voltage characteristic, then it always form a pitch hysteresis loop, which crosses at the 0 values. So and it is also have, if we increase the frequency of the periodic signal, it will the lobes of the this pitch hysteresis loop will shrink, and if we increase the frequency, you can see that the frequency at the 100 Hz it has the more lobe area, but as we increase the frequency, the lobe area will shrink. So these are the fingerprint device which shows this kind of the property. Then it comes into the memory systems, memory devices. So this is the basic structure of the ideal memristor, which is fabricated in 2008 by in the HP labs. And they basically sandwich a TiO2 layer between the two metal electrodes. Here the platinum metal electrodes are used in the HP lab, and they created the oxygen vacancies, engineered oxygen vacancies by the process of the annealing and another processes. So you can see that instead of the charge, they basically generated the oxygen vacancies here, and basically the oxygen vacancy will work as the conducting carriers for the membristors. So the dimension by which in which the oxygen vacancy is created is W, and the whole dimension of the device is D. So if these oxygen vacancies are positively ionized, means if we have O2 plus or O2 2 plus, then if we apply a positive voltage here, then these positive ionized oxygen vacancies will repel and extend towards the next towards the another electrodes, and you can see that the whole layer will be conducting. So this is basically a insulating layer this is a conducting layer, but when we apply a positive voltage here, this oxygen vacancy extends and the whole layer become the conducting layer. So it can be realized as a R on resistance of, can be considered as a resistance of this layer is R on, which is position dependent. That is R on. If you want to determine the whole resistance of the device, then RT can be realized as R on, the R on which is dependent upon the W by W's. So it is conducting width dependent, and R of, that is the insulating layer thickness, and that is also 1 minus W by D. So these are the, if you want to draw the characteristics of this memristor, then the current voltage relation can be realized as the R on W by D plus R of 1 minus W. So you can see that the resistance of the device is basically position dependent. Here the position of the oxygen vacancies are determine the resistance of the resistive part of the device, and this the position, if we derivate it, the relation V is equal to mu into E, then the dW by dt will become mu into E. E is further divided to V by T, that is the voltage across it, and divided by the thickness of the device, and V further is represented as R or R into I. So here you can see that the instead of the charges, oxygen vacancies are basically used as a conductive materials, and you can realize this structure with the help of the any type of the transition metal oxides. Here the TiO2 basically used, but any transition metal oxides, it can be HFO2 or Si or any transition metals P2 P2O5. You can realize this kind of the dice of the memristor. And here is the another structure of the memristor, which is basically similar to that of the your MIM structure, metal insulator metal structure, but here the oxygen vacancies are generated with the help of the electroformation process. In the electroformation process, we basically use a high voltage, apply a high voltage for a certain duration, in which the conductive filament of the oxygen vacancies are developed here. So basically these oxygen vacancies are basically a conductive in nature, so it will also work as a metal, conductive metal, we call it basically a conductive filament, have the same nature that of the metal, because these are the basically very high conducting in nature. So in our basic structure, we apply a high voltages for a certain duration, and we develop a conductive layer. This is a one-time process. There is no need to develop the conductive filament, apply the again and again. We just when we have the fabricated device, we have to just one-time program it. Means one time you have to apply the electroformation process, and there are basically several conducting paths are developed here, but we assume that there is a lumped part, there is a hole in a single conductive filament, but it is there is a gap between the conductive filament and the another metal electrodes, and this gap basically has a certain useful for us to determine the switching behavior of the memristor. So basically this conductive filament is fixed, there is no change at all, but when we apply a low voltages, after the electroformation process, then there is a small barrier here which is known as tunneling barrier. So electrons will tunnel from this side to this side and this side, and from the conductive filament to the another electrons. So this voltage gap is determined by the voltage, the applied voltage across the memristor, and this, and minus I into Rs. I is the tunneling current, and which is passing through it also. So I into the resistance of this conductive filament, which is realized as the Rs. So these are the basic, actually these are the basic structures of the memristor. Now you can see that how the memristor can be applicable to the various applications. There are the vast application of the memristor. Either it may be used as a crossbar array, or it can be used as a discrete part. So even neuromorphic applications have the very vast and very research. Very most of the research are going through the neuromorphic application of the in this time of the for the memristor. It can be also used as the content addressable memory, non-volatile memory, logic circuit, chaos circuit. So there is, you can see there are vast applications of it. You can realize a number of the cellular neural network, differential comparator, any circuits with the help of the memristor. So basically, I have chosen here the memory part of this memristor out of these applications to show you. And so there are the certain circuits of the memristor based memory cells are shown here. You can see that there is a hybrid cell which is used the MB polarity, and this cell shows that the have the high superior performance as compared to NAND and NOR flash. And this is the another structures in which this is basically a DRAM type of the structure in which the capacitors is just replaced by the memristor. So you can see that it is a very scaled device. This is only 10 nanometer, where the capacitors have the higher dimensions as compared to this 10 nanometer. So it can be just one T1R cell of an array structure. When we make an array of this one T1R, then it will be surely give the high density of the design of the memory. And here is the another structure. This is the basically a 60 SRAM, and here you can see that there is a memristor is added along with a control transistor. So whenever the power will went off, the charge stored in this node will be restored to the memristor, and when the power backs, and the stored information will be written back to the node value. So these are the basic applications of the memristor. So first of all, we come to the modeling part of this memristor. How can we model the memristor? And then the model of the memristor is applied to the circuit level. So you need to develop a mathematical model first of all for this, and if you want to use it in the circuit, in integrated circuit, then surely you want to work with the HSpice, and you have to develop the Verilog code for the modeling of the memristor, and then you have to implement it to the your circuit with the help of the HSpice tools or any other. So here I will show you how to model this memristor. Basically, this is a metal structure, and you can see that I told you that there is a tunneling barrier. So we just have to model this tunnel barrier. So after modeling this tunnel barrier, it is and it is simulated in the MATLAB to show to realize its IV characteristics, which is compared with the experimental data, and then it is applied to the circuit level. So here we saw that this is the metal insulator and metal structure. So in the insulator part, we have the there is a tunneling occur between this metal to this metal. Basically, this metal is considered as the conductive filament, and this metal is the electrode part. So if any electrons want to tunnel from this metal to this conductive filament, it faces a potential barrier. It faces a barrier here, and this barrier is basically realized as the rectangular barrier, and we can see that if any trap charges or any ions or any defects are associated in this insulating metal, and if they comes to in at the interface of the metal and insulator, they will develop an equal and opposite charge at the metal electrodes. So there is a image charges are developed here. So basically when the image charges are developed here, they basically induces image forces, electrostatic forces, which is known as the, because it is generated by the image forces, so we call it as the image forces. And due to these forces, image potential is built, and this image potential will mold the corner of this rectangular. Initially, basically, this is a rectangular barrier. After the superimposing of the image potentials, these the corners of the rectangular barrier will be molded, and it's shown as a parabolic or any kind of the structure, any kind of structures. So basically, initially we realize here as the we have a rectangular barrier here, and when we apply a voltage across it, which is certainly less than the rectangular potential of this barrier. So when we apply a voltage less than that of, then we know that the Fermi level will shift down. So there is a barrier will also shift down. So it is reduced by the EV x by s, and this part is basically denotes the impact of the image forces. So if image forces, this is basically the image potential, which is realized at the center of the insulator. And we basically here show you the impact of the different types of the different nature of the image potential. If that we can also realize the we don't actually we don't know which type what is the nature of the image potential. So we first consider the three types of the image potentials, and that is the triangular image potentials, the rectangular image potentials, and the parabolic image potential. And we compare these the results of these image potential with the experimental data, and we can certainly match with the and we match with the our experimental data, and which one is the best matches with the experimental data is the best result for us. So basically we first off impose the rectangular image potential. So this is the rectangular rectangular barrier, which is the down by the EVX by S by applying a voltage here, and this part is shown that this is a rectangular, this is basically triangular image potential. So the mean barrier height, and you can see that the barrier which is extended from S1 to S2. So we have to just develop a relation which give the mean barrier height. So mean barrier height is just can be calculated by 1 by delta S. Delta S is nothing but the S2 minus S1. That is the limit of this barrier from which it extends from S2 to S1. And we can, if we integrate this barrier from S1 to S2, it will give the mean barrier. So our mean barrier will become this 1 by delta S, means S2 minus S1, which is extended from S1 to S2. And if you want to realize the mean barrier height, we just have to calculate the S1 and S2, the value of the limits, that is the from where it is extend the value of S1 and as well as the value of S2. If we have the value of S1 and S2, we can easily integrate these relations and come to our results. So in order to calculate the S2 and S1 values, we can just apply the two conditions when x is less than s by 2, when it is and when we have the s greater than x by 2. then we can easily calculate the value of the S1 and S2, and we will put back them to our original mean barrier equation, and we will come to the final relation of this mean barrier height. Then yeah, parabolic image potential can also be applied, because we are initially considered the three image potentials: triangular, parabolic, and the rectangular image potentials. So we just find out the results for all the image potentials, mean barrier heights for all the potentials, and then we compare with the experimental data. So here we can also include the parabolic nature of the image potential. So the remaining equation is similar to that of the triangular image potential. The only difference is that here we use the parabolic nature of the image potential. So x by s 1 by 2, it is imposed here over the rectangular barrier. So we have need to calculate again the value of S1 and S2. So this is basically a second order quadratic equation. We can say quadratic equation, which is easily can be solved and find out the roots. So roots will give the value of S1 and S2, and the mean barrier height will come. And finally we have the rectangular image potential. So we just this is the rectangular image force. We just ignore the all part, and we included that there is only rectangular part here at the barrier. So the rectangular part is considered, and the value of the S1 is you know that it is 0, and S2 is equal to S for the rectangular barrier, because there is no. So now, whatever we have the mean barrier heights for the three cases, we will just apply to the tunneling relations that is developed by the Simon tunnel model, which uses the probability concepts and the more rigorous correlations to develop the tunneling current. And in his model, basically he used the tunneling to determine the mean barrier height. He uses the probability density functions and another complex formulas to derive the mean barrier height. But by this method, you can just easily model the mean barrier height and just put it into these relations, which will give the tunneling relations. These are the basic parameters which are often used here to determine the tunneling current. So you can just determine the tunneling current, and then the effect of the tunneling current of the barrier heights are shown here. Basically, the first graph represents when the barrier height is considered as the 1 electron volt. Second is shown for the 2 electron volt, and this is the 3 for the 3 electron volts. And we can saw that these graphs are drawn for the rectangular by imposing rectangular image potential, parabolic and triangular, and the hyperbolic image potentials. Basically, you can see that the triangular image will have the that is rectangular barrier, means it suppresses the foremost, and that's why it has give the maximum current, whereas the rectangular image potential will give the minimum suppression to the barrier, and it will give the lowest current. And as we increase the rectangular barrier height, this is for the when the rectangular barrier is 1 electron volt, when it is shown for the barrier is 2 electron volt. So when the rectangular barrier is 2 electron volt, the current density also decreases. You can see that here the current is comes up in the level of 10 to the power 7, but here we have the current which is about to 10 to the power 3. So current is also reduces as we increases the height. But the same nature is appear in every graph, that the triangular image potential will give the render the high current, whereas the rectangular image potential will give the lower current. These graphs are basically shown the impact of the silicon insulating layer thickness. This is for the triangular image potential, this is for the parabolic image potential, and this is for the rectangular potential. So if we increase the heights, we increase the thickness of the insulating layer, that is from 10 to 30 nanometer, 30 to not in nanometer, 10 to 30 angstrom and 30 to 60 angstrom. This can see that the current will reduce. So in the bridge, the current will reduces, will increases the, which is often, which is basically often, which is used to realize the current. And now we have to check the IV characteristics of the memristor. So in order to check the IV characteristics of the memristor, we just develop the spice model for memristor by employing the same by the current relations what we have done for the three cases, and we just apply it into the test circuit. In the test circuit, we just apply a voltage here, a triangular pulse, and also we have a resistance or resistance here. And in order to determine the switching dynamics of the memristors, basically tunneling current, we employed the tunneling relations here. You can see that this is the current appear here, basically tunneling current, which is developed by us in previous slides. And these are the very basic parameters R off, R on. These are basically used the fitting parameters which are derived by the various driving forces. Fitting parameters which are needed to realize the actual behavior of the memristor. So after applying this test signal to this memristor, we can see that these types of the pinch history will appear at the simulation part. So we compare with the experimental data when we impose the triangular image potential. So we can see that here the graph shows a high peak with respect to the experimental data. Experimental data are shown in the blue. So, and if we apply imposes the parabolic image potential, then it is seen that it's very similar to that of the experimental data. Also, it mostly matches with experimental data. And if we apply the rectangular force, then because it has the less tunneling current, it is lower. The off state is lower as compared to the experimental data. So you can see that here the best matching is, you can say that best matching is appear for when the parabolic image potentials are imposes. Now you can also model this MIM structure by considering the different metals. Because the one is the platinum, because you can see that one side of our device is a platinum electrodes, and another side we have the conductive filament. So basically these two metals are not same in nature, because this is another metal, this is another metal. So if we consider the work function of this metal is psi 1, and work function of this metal is psi 2, then obviously there is a work function difference between them, and this work function difference will develop electric field here, and thereby the nature of the rectangle barrier here is not basically a rectangular. It is a certain type of the trapezoidal barrier instead of the rectangular barrier. So if we consider the height of the barrier is phi 1, then the height of this barrier, barrier of this side is equal to phi 1 plus psi 2 minus psi 1. That is work function difference as phi 1 plus del phi. So you can also model the mean barrier height by considering the trapezoidal barrier, but here you have to just need to model it for the forward and the reverse bias differently, because since it is not a rectangular barrier, so the electron tunneling from this part to this part or this part to this part is different, may be different. So it needs to be derive the relation for the forward as well as the reverse bias. So for the forward bias, we just apply a voltage signal here for the of the electrode we have, which have the higher work function, and if we apply voltage with the lower work function, it will work as a which it will work as a reverse bias. So for the forward bias characteristics, we have to work with this metal electrodes. So phi 2, and this is the applied voltage, and this is the basically the barrier work function difference. That's the barrier difference, barrier height difference, and the things is also applied here. The triangular image forces, and then we have to need to calculate the value of S1 and S2, and then finally we have to determine the mean barrier height. In the reverse bias, we should work with the first here. So we have apply the voltage here, and then we have the relations for the mean barrier height, and then we can calculate the S1 and S2, and then we can also apply for the imposing the parabolic image potential in the same manner. We calculate the value of S1 and S2, and then finally we get the value of the mean barrier height for the rectangular as well. So you can when we apply to these mean barrier height relation to the tunneling current relation, we just observe that the current density with respect to the voltages, we can see that the nature of the nature of the image potential variations. So here we have the same current will appear for the highest current appear for the triangular barrier, and lowest current is appear for the rectangular barrier, and this is basically drawn for when the thickness is basically to 20 angstrom. This is basically when the insulating layer thickness is the 30 angstrom, and this is for the 40 angstrom. And it is one thing it is observed that the decrement in the current when we go from this 20 nanometer, 20 angstrom to 30 angstrom, there is a same amount of the difference is seen. What is seen in the for the 20 nanometer, 20 angstrom, and also we have the same, almost not exactly same, but we have the same gap is shown here, is seen here also for the 40 angstrom. This graph shows the variation of the work function difference. That is how the barrier height along with the difference in the work function which impact the current. So this graph is shown for the triangular image potential. This is for when employed the parabolic image potential, and this is for the rectangular image potential over the trapezoidal barrier. So you can see that the first we consider the phi 1, that is phi 1 signal electron volt, and del phi is 0.5. Then second one shows the phi 1 is 1 electron volt and del phi is 1 electron volt. So when we increases the del phi, that is when we increases the work function difference, the current will reduce, and also if we increase the barrier height, the current will also reduce. So this kind of nature we can be are observed. This graph basically shows the impact of the insulating dielectric constant when we increase the dielectric constant of the material by keeping the constant barrier height and constant work function difference. You can see that when we increase the barrier height, the current, when we increase the electric constant of the insulating material, the current will decrease. Finally, we employed the design memester to the test circuits in the SPICE model, in the form of the SPICE model, and realized its IV characteristics. So you can see that when we apply the here also when we apply the parabolic image potential. We have only 0.5% deviation is seen in the off switching. Only 0.5% is observed. Means it is when we observe, when we derive the mean barrier height with the help of the by imposing the parabolic image potential, it will give the best results. Finally, this is the memory part of the memory star. So whatever is the design memory star is modeled, and the model of the memory star is called to the very to the HSpice by modeling by defining it in the Verilog. We just call the Verilog file from of the memory star model here, and the transistor are used here are basically modeled by the model used here are basically the PTM models of the 20 nanometer node. So basically, this is structure we have to we employed the two memory star here. The first memory star is employed at the at this node, that is the source node of the Q1 and Q3, and another memory star is employed with the at the data node with a control transistor. So basically, this transistor, this memory star will help for the read and write operations of this SRAM cell. And basically, this is added for to increase the value of the static noise margin, that is read noise margin and write noise margin, because the noise margin is the important property of the memory, which basically defines the amount of the noise can be tolerated at the input side, so that the output will not be defected. So it is basically when we perform the write operation, it is kept in the high resistance state, and when we perform the read operation, we kept it in the low resistance state with the help of the control 3. This node is connected with the another memory star. So whenever the power went off, the whole information is stored in the memory star, and when will the power come, it will return to the node. So this can be understood by this graph. So initially, this is basically the explanation for this memory star, that is M2, which is connected to the data node. So initially, in the initial state, the control 2 and control 1, both signals are 0. So there is no direct link between this node and this memory star, because this transistor is off. So there is no link between the memory star, no connection between the data node and the memory star. And in the store state, we just make the control signal 1. So the transistor, this transistor will on. And when this transistor will on, the whole information is stored in the same information is stored in the memory star. And in that case, the control 2 is still 0. So when the power down, the whole power is down. The whole power is down means the WL is equal to 0, VL is equal to 0, VDD is equal to 0. So the data node will become 0. This node is also 0 because this is static RAM. So power when the power lost, the data is also lost. So, but what happened? This control signal is also 0 because the power is off. So, but we have the information. We have the information in the memory star. That is the previous information which is stored in the memory star. So when the power backs, we have to make there is no need to make the VDD is equal to 1. We just apply a control signal here, and the whole information will be written back to this data node. So this is the condition when the data node is 1, but when the data node value is 0, there is no need to apply a signal because the data is 0. It is always in high resistance state. So we can also prove it by the timing simulation diagram. So this is the control signal. This is control 2 signal, which is applied here. Control 2 signal. This is control 1 signal. These are the bit lines, and this is the word lines, and this is VDD. So we have just plotted all the results with respect to a time. So control 2, control 1, WL. So initially in the storage state, you can see that the control in the storage state, the control 1 is equal to 1, control 2 is equal to 0, and VDD is equal to 1, because we are storing. So our device is on. BL is 1, BLB bit line is 1, bit line bar is 1, and we can see that we have the value at the data node. That is the data node VD is equal to voltage at the data node is equal to also 1. And the data at the Q bar, that is the another node of the SRAM, that is this node DN bar, is 0. So when the power down means VDD is 0. So VDD is 0. WL is also 0. So word line is also 0. There is a word line is also 0. So there is no connection of this node to the bit line and this node to the bit line bar. So WL is 0 means excess transistor are off. This excess transistor is off, and we have power is down. So this control signal is also down. This control signal is also down. So the whole information, the whole signals will down. And when we want to restore this information, we have to just make the power up. So just need to power up. But here we don't have the connections between the node and the access and the bit line. So you can see that the bit line, your bit line bar, bit line is 0, and WL is still 0. So if WL is 0, if WL is 0, so there is no connection between the bit line and this node, and bit line bar to this node. So information cannot be means this data node cannot be written from the bit line side, or this node cannot be written from the bit line bar node. So we just keep the WL is equal to 0, and you can see that when the power's up, we just make the control signal control 1 signal is equal to 1 to make the control transistor on, and we just make the control 2 is equal to 1. So we can see that the whole information is written here, and the VDD is comes to 1. Means the information what is stored in the data memory store is come back to the data node of the SRAM cell. So we can also compare the static noise margin, read noise margin, and the write noise margin. So it can be seen that this cell shows that the 16% improvement as compared to your conventional SRAMs. And because of we had added a memory store at the source side of the SRAM cell, and as this graph shows that as we increases the VDD, the rate margin basically increases in the both cases, but the tendency to increase the this cell is higher as compared to the conventional one. And also you can see that as we decreases the feature size of the transistors, the rate margin is obviously decreases, but the decrease in the value of this cell SRAM cell is less as compared to the decrease in value of the conventional SRAM. Also, the write margin shows that there is 30% improvement, and but it is seen that there is a small power delay. Power delay is more in this 72 SRAM as compared to, but it's not much difference. Also, you can see the write delay is higher as compared to the conventional STRAM, and but it's not much as. But we can see that the power dissipation is low as compared to that of the current flash RAM. So these are the basic applications of the all about the registers and its memory applications. So thank you for listening me. So is there any questions? Is there any question from the audience side?
Any question? Okay, sir. Thank you.
Okay, Ravi, thank you.
वही ऊपर. Okay, next session will tomorrow 11 a.m. कल 12 बजे. कल 12. अच्छा, tomorrow session will 12 p.m. 12 p.m. Okay, thank you. Okay, thank you, sir.
Okay, thank you, Ravi.
ममता मैम एंड आशीष रमन सर, ये मीटिंग अच्छा